So we did it with a very small system. As you can see, this is much smaller than the one we would use it. The distance was 2.5 centimeter. The slit were 12 micron with a pitch of 40 micron, and it was 100 micron thick. The P-bar energy was much higher than we would use it. Nevertheless, we were able to measure the force acting on these antiprotons, and we published 3 years ago. We had a light reference system in which you measure the alignment on your system as a comparison, okay? And we shoot antiprotons into this system. We were able to measure the annihilations of the antiprotons. And in this way, we measure the fall of these antiprotons. Let's state clearly that this is not due to gravity. At such speed, gravity is 0. Clearly, this was due to electromagnetic forces. This is an example of an antiproton annihilation. We used emulsions with very high resolution, with 1 to 2 microns. We were able to detect clearly 146 antiprotons. And here you see the picture I showed you before, in which you have the light distribution and the antiproton distribution. You see that you have indeed a shift of about 9.8 micron. We have a not small systematic, but nevertheless we've been able to measure a deflection of about 10 microns. These correspond to a force of about 530 upton-newton, consistent with the magnetic field perpendicular to the speed of 7.4 G Gauss, and indeed the measurement we did in that position was about 10 Gauss, so it's compatible with the force due to magnetic field. But this is not important. We were not going to measure the force. We were trying to test our system, complete system, to see if this could be used for the real measurement. The other big step that nobody did before was to produce positronium and also to excite positronium. So how do you make positronium? You make a positron beam, you hit a silica target in which you made some holes, nanochannels. This with a diameter of 5 to 10 nanometer and a depth of 2 microns with special systems. And the positrons can go inside into these nanochannels. They are slowed down, they interact with the electrons, and in 30% of the cases, positronium comes out. We tested it, this system, with a pulse measurement, and we did 2 measurements actually. We were hitting the positronium beam on a passive surface and on an active surface. And we were measuring the gammas that were coming out of the annihilation of the positrons. This is the curve with the passive system, and this is the curve with the active system. You clearly see that you have annihilation at a longer time because the positronium lives longer than the positrons. About the lifetime is about 142 nanoseconds, and this is compatible in this with the production of positron. But the difficult thing is not to produce it, but to excite it. So we were doing a disappearing experiment. We're doing, on top of using the passive target, we were using an active target in 2 ways. In one way, we were simply shooting the exciting laser. It's a UV laser from n equal 2 to n equal 3. And the second time we were shooting this laser plus another infrared laser to ionize the positronium. If your positronium is there, and if you have been able to produce it, then you would kill it. And measuring the area between the laser, infrared laser on, that's this lower curve, and laser, infrared laser off, and measuring the ratio between the two, and scanning the frequency of the UV laser, indeed we saw that we were producing excited positronium, about 15%, the overall efficiency between excitation and ionization. Then we did also another measure, since we know the positronium n equal 3 was there, we tested it also if we were able to pick a specific n and excite the positronium at the specific n, and indeed we saw that we've been able to excite to n equal 15. Okay. Positronium, the flight, antiprotons. Actually this is something that we do routinely since many years, but recently we made some nice measurement, a nice publication, in which we saw clearly this is two dumps. You repeat the same experiment. You have antiprotons, you merge with electrons, you cool them down, you let them do for a while, and then you dump. In one case you dump electrons, you do the same, and then you dump antiprotons, and you see how it goes. When you dump electrons, you see this shape. When you dump antiprotons, you see this shape. You clearly see the radial, that the antiprotons, due to centrifugal forces, at the end ends up in the side of an electron cloud. So they are slowed down, but then they end up to be out. Well, it's centrifugal forces, the mass is bigger, so they go in the outer shell. This is something that you do not want, because otherwise they are too weak. You cannot mix it with positronium. It's much better to have it in the center with a high density. And this we achieved to do this with some technique called rotating wall. Some electrodes are split in 4, and so you make a rotating electric field, and you make your electron cloud to spin. In this sense, in this way, the clouds get smaller. We've been able to achieve a density of 2 × 10⁻13 per square meter antiproton. This is the lowest antiproton in a radius of 170 micron. This is the lowest antiproton cloud radius and the highest density ever. So this is something we are going to use this year to try to produce anti-hydrogen. Y ahora, así que... Bueno, las conclusiones es prácticamente lo que dije durante la charla, así que la dejo a ustedes. Gracias por la atención. Esta es la colaboración. Tenemos institutos europeos, University of Brescia, somos nosotros. Una gran parte la INFN, Instituto Nazionale di Fisica Nucleare, y pues tenemos el CERN. El CERN y INFN son los dos grupos más importantes de la colaboración. Esto cómo se crea el positronio, y la respuesta a la pregunta de antes. Stark acceleration was done in 2006 by Merck, the group in Zurich, and they are in satellite of our expense, so whenever it's needed they should join again. So the energy levels of an atom or an antiatom in electric field are given to the first order in atomic units to an energy that depends on the quantum numbers. So if you go in a place where you have an electric field gradient, then to compensate from the energy, then you end up with a delta kinetic energy. It can be in both directions. That's why some of them you decelerate, some you accelerate them. But in this way, you are able to accelerate to horizontal velocity of few hundred meters per second. with an electric field of few hundred volts per centimeter.
And you are taking data this year, 2018?
Yeah.
Because you're stopping LS2?
Yes.
Okay.
This is our last chance to make anti-hydrogen this year. We may come back in a few years, but
it started right now.
Monday.
Monday.
Yeah.
So you probably have made already very calculations of how much statistics you need to make a significant measurement on the.
Yeah, with few you need a few hundred of antiprotons. So
not that many. So
not
that's
that
good.
many. But this year we won't make any gravity measurement for sure, because our goal is to make anti-hydrogen in this way and to accelerate it first. Then, if we are able to do it this year, then we plan our data taking in 3 years to be able to do the measurements.
Why is in 3 years? You have to wait to build the...
Separan 2 años.
separan.
2021, 19 and 20, all CERN accelerator are down, as you know.
This is the same principle as alpha is using to measure the energy levels, or?
No, well, similar. What they do is actually to merge directly the positrons cloud and the antiprotons. Actually, they prepare. This is the way we were doing in Athena. Athena was the.
No, I mean this principle of the effect of.
They produce anti-hydrogen and they are able to keep it with a gradient of a magnetic field, because every hydrogen or anti-hydrogen atom has a dipole, magnetic dipole. If you have a gradient of a magnetic field, you are able to trap them. It's very difficult, but they are able. Then they keep it there. Then they shoot laser at different energy. So when they with a correct energy, clearly you kill the antiproton, you take away the electron of the antiproton, of the antihydrogen. Then it comes out and it dies on the wall, so you see it. So if you scan in a laser frequency and you study your annihilations, when you find the correct energy, you see a maximum in the annihilations. And in this way, scanning, they were able to see the energy levels with quite nice precision of the levels.
And the result is that the CPT holds.
Yes.
By now.
By now.
We would know otherwise. We would have heard, I suppose.
Clearly, this is a direct measurement. Indirect measurements are, for the moment, more precise, but there are implications about the basic principle you assume. This is a direct measurement, and at the moment it holds. At the moment they didn't see any difference between the levels in hydrogen and in antihydrogen with the precision they have.
And your data, which comes from PS, doesn't interfere anything with the LHC?
No.
You can, LHC is working and you can get data from PS?
Yeah, because basically they get one every 120 seconds. So one speed, I don't know how it works, but
okay.
and then I believe that in LHC you inject the beams and then for 12 hours you keep them.
You close for the SPS and then, yes.
In fact, in SPS there's a lot of test beams as well, which do not interfere
with LHC.
In the part of the antiproton trap, I didn't get how you kick out the electrons but not the antiprotons.
Because you do it fast and the mass is different. So
how fast is fast?
You know, acceleration is force divided by mass. If the mass is lower, the acceleration is higher. So if you are fast enough, how fast? Nanoseconds, tens of nanoseconds. But the antiprotons are much slower in reacting. So if you do it fast, the electrons comes out and the antiprotons stays in.
So looking at this plot here, then I don't know if this is a real one, is what you expect in the experiment, but isn't it a problem if this distribution is asymmetric, because it could be giving you an asymmetric spread later in the spatial spread.
No, because in principle you are able to measure one by one.
Ah, okay.
You measure the time of flight, right?
Yeah, time of flight. Because the time of flight is 2 milliseconds, so clearly you measure it very precisely, in order of nanosecond you're able to do it. So that shouldn't be. Clearly you can slice your distribution. This is reproduced by this distribution of time of arrival. This is actually the speed, the time. This is velocity, this is the square of the time in milliseconds squared. So then clearly you have to have enough statistics, you have to slice depends on how statistic you have, but if you slice then and you consider the center of the beam, you can correct for this.
Just curiosity, in the case of I think that in case of anti-hydrogen atoms, the maximum time they can have them without being alkylated, it's like 15 minutes. In the case of the positronium, how much time can you have them without being alkylated?
Wow, it depends on the good vacuum you have, but in principle you can have it for hours, days. If you are good enough in the vacuum, it depends on how good you are in the vacuum, but that's not a limiting factor. Even in the anti-hydrogen now, they keep it for a long time. At the beginning it was few seconds, and then they improved. Now
The level of vacuum is the same as the LHC, or
sorry?
the level of vacuum is the same as we
No,
use it?
better.
Better, much better.
Oh, that's pretty good. With a small volume.
Clearly, the volume is
Yeah.
But it's
many order of magnitudes lower, because LHC is 27 kilometers, and here is, let's say, a few meters. I don't remember badly, 10 to the minus 12 millibar or so, but I shall be.
how do you achieve a vacuum like that?
You pump.
Ion pumping.
You
Ion
pump.
pumping.
Yes, and you pump and you keep pumping. But of course, clearly at 4 Kelvin it's easier than
Yeah.
temperature.
Yo quería hacer un anuncio en español, que es que Germano esta tarde da el café científico sobre otro tema, pero si quieren ir va a estar entretenido seguro también sobre, bueno, rayos cósmicos, tomografía, quizás con muones y...
Me invitaron, no me hace trabajar.
Claro, sí, que nadie viene aquí de gratis.
Muchas gracias, hermano.
A ustedes.